this circuit is nothing but this circuit, with this VDD being nothing but a battery connected like this, because it has a positive value. I connect it like this. Alright, and this ground is nothing but a common wire with 0 voltage in relation to any other voltage in this circuit. Now I'm asked to find how much will this VG be, just so my MOSFET device is in saturation barely, alright, at the edge of saturation. While I'm given some values for the MOSFET, and I'm given this VDD and the RD. Alright, and I have two cases where I have channel length modulation and where I don't have channel length modulation. Alright, I'll start with a simple one where I don't have. And I'm going to say that, well, for saturation, I know that always these two conditions must hold. VGS, the voltage here, minus the voltage here, must be more or equal to VTH. And VDS, the voltage here, minus VGS, must be more or equal to VTH. These are very, very fundamental. If you don't know this, check out my video on the basics of the MOSFET, so you can have a better foundation. Anyway, the edge will be given when this is equal to this, all right? And I know that VTH given from the exercise is 0.4 volts. And it happens that VGS is the same as VG. You see why? Voltage here minus here is the same as VG. It happens because we don't have source degeneration. We don't have, let's say, any resistances here. All right? Now, I'll say that this loop here, name it L1, is going to give me something very insightful when I do a KVL here. I'd say that when I enter the negative terminal, all right, this VDD, it's going to be this in this part of the equation, is going to be equal to RD hiding, the voltage drop here. Why? Because the current flows like this, right? If it flew the other way around, RDAD would be in this part of the equation with a plus sign. It's going to be plus VDS, all right? It's VDS because it's VD minus VS, so it's plus and minus here. And now I separate things like this, and I have VDS is VDD minus RDID. This is the equation 2. This is a very, very basic KVL, all right? We're careful with the polarities. And now I know from theory that the current that's flowing through the MOSFET, all right, the ID is going to be obviously the same as IS, no current flows in the gate or from or through a gate. And it's going to be equal to 1 over 2 mu NCox W over L VGS minus VTH squared. This is for the for when I don't have channel length modulation. All right, because I know I'm in the saturation region, all right? And I'm going to replace some of the values here from these that are given by the exercise. All right, VTH is 0.4, and the other values is simply given here. Also, be careful with the CMU NCX is given as microamps over voltage squared. So very careful to transform this value into the SI measurement. Now, with this out of the way, I can just do some simple algebra here, and I have that ID is equal to something VGS minus 0.4 squared, or VG. Now, I can go and replace from 1 and 2, all right, you see why? The ID is this ID. ID is equal to VDS minus VDD with a minus in front of RD, and I know that VDS is nothing but 0.4 plus VG. So I replace everything here. VDD is nothing but 1.8 volts. I know RD is 5 kilo ohms, all right. I replace everything as is. Again, I'm careful to put a 5 kilo ohms, not 5 ohms, all right? 5 times 10 to the power of 3. And when I do the algebra here, I have nothing but a common quadratic equation for VG, where I will have two roots where I have the value, where I get the value of VG. Hopefully you know how to solve quadratic equations. And VG is going to be equal to either one of these two values. Now, because I know I'm in the saturation region, VGS or VG in this case must be more or equal than VTH, alright? How much VTH? 0.4. Therefore, only this value will be accepted. Usually, only one value of not usually, always, when we solve this type of equations, there is going to be only one value for VG that's going to be acceptable. All right. Even when we have more complex configuration here, only one value for VG is acceptable. All right. Now we're asked to do the same for when we have channel length modulation. I'll just write the previous value here. No reason for now, just so we remember it. Much of the same analysis will be done again. All right, it's the exact same as what we did before up to the KVL. All right, nothing really changed here. And the only thing that's changing when we have channel length modulation is the current that we have from theory. We have the same current here multiplied by 1 plus lambda times VDS. Now you see how much this circuit became very, very complex very, very quickly, because now I have a dependence of the current to this VDS voltage 2 instead of this simple VG that we had earlier. I'm going to replace VDS with this from this, all right? It's going to be nothing but 0.4 plus VGM, all right? 0.1 is the lambda. Again, I replace the same values here from before. And again, like before, I go from here and here and replace the values over here for the ID. These are the exact same as before, exact same analysis. VDD is 1.8, all right? And I do some of the map here, so I can have clear values and have a more clear image of what's going on. I have something constant, minus Vg over something, must be equal to Vg minus something squared times something plus Vg plus Vg, right? This is a cubic level polynomial, all right? Things got much harder, much more quickly with this addition, all right? And you can try and solve this, all right? You can solve this. In this case, you're lucky because we have a simple cubic relationship, a cubic polynomial, and you can use Cardano's rules or whatever to solve this. But you will not always be lucky. You will not be always able to solve this this way. So what I'm doing is going to be a universal way to solve this, and pay very close attention to it. This is universal, so no matter how complex this is, you will be able to solve your circuits with MOSFETs like this. So we thankfully were asked to find how much Vg is going to be when we didn't have channel length modulation. I suspect because lambda is not very large, that the value of Vg now is not going to be much different than the value that was before, alright? I expect it to be a bit lower, but not much different. So what I'm going to do is I'm going to try to see what this and this part of the equation is going to yield me when I replace Vg with the value that I found earlier when I didn't have a channel length modulation. When I replace the values here, I get that this part of the equation is equal to this part of the equation. They are not really equal. This equal sign is not really an equal sign, all right? But it's good for us to visualize what we are trying to do here. And I see that this part of the equation is smaller than this part of the equation. All right? A bit smaller, all right? So obviously Vg is not going to be the same as before. Well, what if I try a slightly smaller value, because I know the voltage of the gate must be a bit smaller, and I try this value, 520 millivolts, all right? I replace again this value here, and thank God, this part of the equation is higher than this part of the equation, all right, this time. If it wasn't, if again this was smaller than this, I would have to try an even lower value, and an even lower and lower up until I have this. Now, I know it, that the solution, the final solution, must be between these points and this point. I know that Vg must be confined between 520 millivolts and 526 millivolts. All right. I try the middle value, 523 millivolts. I do this for the up to 4 decimals to check my accuracy. And you can do whatever you want, like this one I prefer for this exercise. So unless we are given the decimals that we want for our results, we will assume it's a reasonable value. So up to the 3 decimals for my result, which means that I will do the analysis for up to the 4 decimals in my equation. So I have this is something is smaller than this, all right? So now I can check in a much smaller area, all right, between this 520 and this 523, all right. The area where I look for is much smaller. All right. If this was higher, if this was higher than this, I would have to check between this value and this value. Now I take a random value between here, so I take something between this and this, which is 521, and voila, I have that this part of the equation is the same as this part of the equation. So up to the 4 decimals, I have a very good accuracy of this approximation. All right. So I know that Vg must be up to 3 decimals, 521 millivolts. All right. Let me see it holds. Okay. And that's it. I found my final results. If my exercise asked a result for up to 4, 5, 6 decimals, I would have to keep going and going up until I got my desired accuracy. Check out the other videos from my MOSFET playlist and subscribe to the channel for more electronics videos. Study well and take care.